In this video, we're going to look at something called LHopitals Rule. Now, LHopitals Rule is a way to evaluate limits of a ratio of two functions where when you're looking at the form that it takes, you have an indeterminate form of either 0 over 0 or infinity over infinity, and it could be like negative infinity over infinity, infinity over negative infinity over negative infinity. So any of those types of forms. And in this video, we're going to look specifically at what LHopitals Rule says and maybe do a couple different examples. And then after that, I'll have a separate video that even does more examples in addition to the ones presented here. So let's just look at what LHopitals Rule says first. So for LHopitals Rule, it says let f of x and g of x be differentiable functions on an open interval from a to b containing c, except possibly at c. So it is something that might not be differentiable right at the value that our limit is approaching, and that would still be okay. And let g prime of x not equal to 0 for all x in that open interval from a to b, except possibly at c. Now, if the limit as x approaches c, this same value that we were saying that it might not be differentiable, the functions might not be differentiable, and g prime of c might equal 0. And if that limit as x approaches c produces an indeterminate form of either 0 over 0, infinity over infinity, negative infinity over infinity, infinity over negative infinity, or negative infinity over negative infinity, then the limit as x approaches c of f of x over g of x will be the same limit as x approaches c of f prime of x over g prime of x. Now there's a couple things that I want to bring to your attention here. First thing is that this rule only works if you have one of these indeterminate forms. So if you get a 0 in the numerator as x approaches c, but not a 0 in the denominator as x approaches c, then that limit actually is going to go to 0, and you don't need LHopitals Rule. Plus, it hasn't met the conditions of it, so it wouldn't give you the right outcome in most instances. If you have a non-zero number in the numerator but a 0 in the denominator, then you have it where that limit's not going to be defined. Again, it's not meeting one of these indeterminate forms, so LHopitals Rule is not going to be applicable to that situation. It's only when we have the 0 over 0, infinity over infinity, etc., that LHopitals Rule gives you the accurate result of that limit. I also want to mention that there are some other types of expressions that we will add to that can be transitioned into an expression, and then if after you transition it into that expression you get an indeterminate form, you'll still be able to use LHopitals Rule. They're just not listed in the original rule. And then the last thing I want to mention about this before going to the examples is that even though that is a quotient, we're not talking about taking the derivative of the overall quotient. Those sorts of situations, the derivative of a function that is a quotient of two functions, we would need to use the quotient rule if we just wanted the derivative. And remember, the derivative of a function is you put a value in and you get the slope of the tangent to that original function out. This is trying to find the limit of the ratio of two functions. So I'm looking at the numerator separate than the denominator, and I'm taking the limit of these, and that's when I can apply LHopitals Rule. So I'm actually just differentiating the numerator as a completely separate function as the derivative of the denominator, and I'm not taking the derivative of an overall quotient. That would need the quotient rule. This just needs the derivatives of them individually. So this is true provided that limit exists. Now, if once I do the application of L'Hopital's rule and I take the limit as x approaches c of f prime of x divided by g prime of x, and then I go to try to evaluate the limit, and I find out that I still have a 0 over 0 case or an infinity over infinity case, etc., then I can use L'Hopital's rule again. So there will be certain situations where we will apply L'Hopital's rule more than once to get our outcome. So my first example, I'm looking at trying to find the limit as x approaches 0 of negative 12 sine x over x. So I want to think about these limit questions from the very beginning of the types of things we did with limits and think through the process and evaluate what I might be looking at in this situation. And then if I do in that investigation get a 0 over 0 or infinity over infinity, etc., I'll apply L'Hopital's rule. So remember, when I have a ratio that I'm trying to find the limit of, I'll look at what the value of x is approaching and see if I get a non-zero number in the denominator, or if I get a 0 in the denominator. So the limit as x approaches 0, if x is approaching 0, then x is approaching 0. So my denominator is approaching 0. So I just designate that off to the side in front of it, just saying, well, there's the 0 in the denominator when I'm looking at what it approaches. Now, how about in the numerator? Well, as x approaches 0, the sign of a value approaching 0 itself approaches 0. And then if I take my negative 12 times something approaching 0, that will also approach 0. So here I get my numerator is approaching 0, my denominator is approaching 0. So this is a situation that fits the requirements for L'Hopital's rule. So now it says that the limit as x approaches c of f of x over g of x will be the same as the limit as x approaches c of f prime of x over g prime of x. So we're going to still write the limit as x approaches 0. And then we are going to first take the derivative of negative 12 sine x. The derivative of negative 12 sine x is negative 12 times the derivative of sine x. And the derivative of sine x is cosine x. So my derivative of my numerator is just negative 12 cosine x. And again, because we're applying L'Hopital's rule, not differentiating a quotient, we're applying L'Hopital's rule, we're going to look at the numerator separate from the denominator. Now, what about the derivative of the denominator function? Well, the derivative of x is 1. So now I'm really looking at the limit as x approaches 0 of negative 12 cosine x. Well, as x approaches 0, cosine of a value approaching 0, well, the cosine of a value approaching 0 approaches 1. And I have negative 12 times 1 gives me a value of negative 12. Now, when you're writing your answer, be very careful to use correct notation. I can't write just the limit as x approaches 0 equals negative 12, because you need to know what function you're looking at for that limiting process. So if you want to write a final result here, you want to write the limit as x approaches 0 of that negative 12 sine x over x is equal to negative 12. Okay? Now, you probably saw another way to handle this problem when you did special limits back in the very beginning discussion of limits, way before you did derivatives. And if you used that approach, you'd get the same answer. It's just another approach to that type of a question. Next one, the limit as x approaches 1 of 4 times the natural log of x divided by 3x cubed minus 3. So think about the denominator. As x approaches 1, then 3x cubed minus 3. Well, x cubed approaches 1 times 3. Well, that would approach 3. Subtract 3. The denominator approaches 0. In the numerator, when x approaches 1, I have to think 4 times, well, what's the natural log of a value approaching when x is approaching 1? So when you investigate that, you'll find that when x approaches 1, the natural log of a value approaching 1 approaches 0. And 4 times something approaching 0 approaches 0. Again, I have that 0 over 0 case, so I can apply LHopitals Rule. So I'm going to have the limit as x approaches 1 of, in the numerator, I have 4 times the derivative of the natural log of x is 1 over x. And then in the denominator, the derivative of 3x cubed is 9x squared, minus the derivative of negative 3 is 0. Now, I have to look at this in terms of a simplified form of it before I try to see what's going on with this. In the numerator, that's 4 over 1 times 1 over x, so that's 4 over x. So this is the limit as x approaches 1 of 4 over x divided by 9x squared over 1. So when I flip and multiply, I have the limit as x approaches 1 of, think of flip and multiply, it'll be 4 over 9x cubed. Now think, what is happening with this limit as x approaches 1? Well, as x approaches 1, 9x cubed approaches 9. So I don't have a 0 in the denominator anymore. And as x approaches 1, my numerator 4 approaches 4. So I get that this limit is equal to 4/9. So then again, if you want to write the final entire expression and then say what limit you got, you will need to write the entire thing, limit as x approaches 1 of 4 times the natural log of x over 3x cubed minus 3 is equal to 4/9. Just to make sure that you have good notation. You never write just the limit as x approaches a value equals something, because there has to be an argument that that limit is being applied to. Well, I hope you've found the discussion of LHopitals Rule and a couple examples helpful. There'll be another videos that I will post that just show you more examples to applications of LHopitals Rule, and also ones that include examples of those types of expressions that in the beginning aren't the indeterminate form, but when I rewrite them in a simplified form, that turns into something that has an indeterminate form that LHopitals Rule can be used on. So we will apply it from there.